All right. Happy Tuesday, week 6. After tonight, we are halfway through the term, and we're more than halfway through the material though, because we have 7, 8, 9, and 10 left. Um, and we're really getting into the nitty-gritty of probabilities and the stuff that is actually useful. Um, seven Unit 7 is like important. It's not some of my favorite, but it's super important for like everything we do from here on out. So it's a real foundational unit. So today we're going to talk about kind of like what things mean. When we find something, what does it mean? We're going to talk about that. We're going to make some connections with the empirical rule and the normal curve. We're going to make those connections, and we're going to talk about area and what these things mean. Um, and very, very little math tonight. On Thursday, there will be a lot of math. You're going to get some fancy calculator functions, and we're going to dig a little bit deeper. There is only one assignment, so 7.1 and 7.2. So there's not really going to be much you can do with the assignment today. So that kind of gives you a little break also. And also to get last week's stuff done, because I think there's a quiz due tonight and the hand-in homework. So you can get those done. And if you have any questions about the hand-in homework at the end, I'm happy to answer those. All right. So there we go. That's what we're doing. We're talking about uniform probability distribution. We're going to graph a normal curve. We're going to look at some properties, and we're going to look at area. And I apologize if you can hear my cat. Maybe if I can get my screen to go to the next page. Oh, I see what's happening. Okay. So a uniform probability distribution, we talked about this probably week 2. So way back when we discussed the uniform probability distribution just a little bit. So what the uniform probability distribution has to do with is that any point on the uniform distribution has an equal probability. So for example, we have a friend who's always late. Um, Oh, look, it says fiend instead of friend. Sorry, I get distracted. So my friend could be on time, which would be 0 minutes late, or he could be 30 minutes late. Anywhere between 0 and 30 has an equal likely chance to happen. So they could be anywhere between 0 to 30 minutes late, and every single one has an equal probability. So he's just as likely to be 3 to 4 minutes late as he is to be 25 to 26 minutes late. So our variable X can be any value between 0 and 30, including 0 and 30, and it's just equal probability. This would be a uniform probability distribution because every point on the graph has an equal possibility of being chosen. So I'm going to show you what that graph would look like in a second. So a probability density function. This is what the PDF stands for on our binom PDF. So it's a probability density function. So we, in order for it to be a probability density function, in order for us to use the analysis methods that we're going to do, our density function, the total area underneath the curve when we graph it, underneath the graph, is going to be equal to 1 because that's 100% of our data. And the height of the graph has to be greater than or equal to 0 because we can't have a probability less than 0. It's got to be greater than or equal to 0. So I'm not going to ask you to give this information back to me, but you got to just kind of know in your knower that this is a thing. Here's my graph. Yes, it's a picture of the textbook, but it was a good picture. So I just took a picture of the textbook, I snipped it, and I put it into this slide. So here, the area is 1. And since he can be anywhere from 0 to 30 minutes late, and each one has the equal probability of happening. So in order for this area to be 1, the time, where's my pen? The time has to be, I don't know why my pen is not penning, has to be between 0 and 30 minutes. So in order for it to be 1, every minute has 1/30th chance of it happening. It says density, but this is also probability. I'm going to put that here too. So there's a 1/30th chance of him being any of these minutes. 1 minute, there's 1/30th chance of him being 1 minute. There's 1/30th of chance of him being 15 minutes. So each time has 1/30th of a chance. So in order to have an area of 1, 30 times 1 over 30 equals 1. So there we go. So this is our rectangle. This is a uniform probability distribution. So sometimes uniform probability distributions are, and this is something that you might just want to keep in the back of your mind. Sometimes they're represented by somebody spinning a wheel, and every section of the wheel has an equal chance of the wheel landing on it. There might be something that comes up on, oh, a quiz or a test or something that has to do with you spinning a wheel. Every stop on that wheel has an equal probability of happening. Now, we're assuming it's a balanced wheel. We're assuming, that each section is the same width and all of that. So assuming all of that. Sometimes we just assume things. All right. So, when we are looking at these probability distribution functions, the area of the rectangles or a section of our graph represents a probability. So I can calculate the area of one of these sections and it represents the probability. So for example, we're looking for what's the probability of my friend being 10 to 20 minutes late. Okay, so remember each minute is 1/30th. And here we're looking at 10 to 20, so I have 10 minutes. So I'm going to math it like this. 10 minutes times 1/30th of a probability is going to be 10/30ths, or 1/3, or 33.33%, if you will. So there's a 1/3 probability, or 33.33% probability that he is going to be between 10 and 20 minutes late. So all I did was find the area of this rectangle right here. Remember, the area of a rectangle is just base times height. And that's all I did here. So once again, let's take a look at this one. So we have the probability here. There's a 20% probability that he's going to arrive between what minutes? So here, I know that it is 1/30th, sorry, times whatever this width of the rectangle is. The width of the rectangle represents how many minutes he's late. We don't know what that is, so I'm just going to use X because X is a good variable. And that's going to equal 20%. So dig way back into your algebra skills. Way back deep into your algebra skills. If I am 1/30th is the same thing as dividing by 30. So to undo division, we're going to use multiplication. So I'm going to multiply both sides by 30. So X equals, so 1/30 times 0.2. I don't know why I put that in my calculator. X equals 6. So there's a 20% chance that he will arrive in the next 6 minutes. Questions on this? Okay, this is a super simple case because most of the time we are not going to be dealing with a uniform probability distribution. So most of the time it's not, but this is a simplified case to show you how area can be connected to probability. So we're going to do it with a little bit more complicated case. Let's move on. All right. So when I draw this lovely little curve over my histogram, we have this nice, beautiful bell shape. It is a normal curve. I've been kind of off and on calling it a normal curve, a bell curve, a normal curve, symmetric. All of that kind of means the same thing. I'm going to try to draw this in, make it prettier. Normal curve, symmetric, bell curve, all of those are basically the same thing. We're pretty much just going to call it normal from here on out. because normal is, it's like the law of the land. Most of the analysis methods that we have, we can't do unless we have a normal distribution. And we're going to talk about how to get things there and what to do with them and everything after this. But I have this beautiful bell curve right here. And notice my histogram, I have all these cute little rectangles under here. So there, I have all of these rectangles under here. We're going to talk about how to use those to try to find probabilities. And since I'm not going to teach you calculus, I'm going to teach you fun calculator functions on how to make this happen. So let's move on. Uh-oh. All right. So because this isn't calculus, we're gonna kind of drop the inflection point thing. I'm not going to even do that. If you've taken calculus or you're currently taking calculus, you know what an inflection point is, and it's really not going to help you here. So we're just dropping it because I'm not going to teach you the calculus behind this. We're going to keep it simple. So if our continuous random variable is normally distributed or has a normal probability distribution, so we have this nice, beautiful bell-shaped symmetric curve. So just picture this in your head. Every time somebody says something is normally distributed, you think of this beautiful bell curve. Now, bell curves have a lot of different shapes. So take a look here. Sometimes bell curves are centered around 0. Sometimes they're centered around another number. Sometimes they're taller. Sometimes they're shorter. But if they're shorter, they're going to be more spread out. But still, if it's symmetric about whatever the mean is, and it has this nice, pretty thing, no major outliers, this is a bell curve. All of these are bell curves. These are all considered normal curves, right? Okay, here's the properties of the normal density curve. Once again, I am not going to ask you to give me all of this back. This is just kind of for you to get an idea and to be able to picture in your head what's going on here, especially if you're moving on to 244, all of this is going to be important. It's a pretty small percent. I probably have, I don't know, maybe 3 students a year, and I teach this 4 times a year, 3 students a year that move on to 244. So if you're not, don't worry, it's not super common. Okay, so properties of a normal density curve. It's symmetric about the mean. So half of your data is going to be above the mean, half of it is below the mean, approximately. The mean and the median are going to, I don't even care about the mode, but the mean and the median are going to either equal each other or be super, super close to each other. And our mode is usually in the middle as well, but I don't really care about that. But you have this nice, pretty peak right in the center because our mean and our median equal each other. It's not skewed right or left. The area under the curve is 1 because 100% of our data is under our curve. So the area is going to be 1. I already said this, that to the right of the mean is going to be 50% and to the left is 50% or 1/2. Right, we good so far? Okay. So now, I don't know if you know what an asymptote is. An asymptote is a line that a graph gets super, super, super close to this line, but it never touches it. That's kind of what happens with our normal curve. So going back here, this right here, so as I'm going to go to this one. No. So as I get close to the x-axis, it doesn't actually touch the x-axis. It gets super, super, super close to the x-axis, but it doesn't touch it. That is because sometimes there are outliers, because remember that there's still that 0.15% that is, or basically 0.3% that is outside 3 standard deviations. So it's somewhere way out there in the tails. We do occasionally have some stuff way out there in the tails. So our normal curve doesn't necessarily touch that axis. It doesn't go all the way down. And as I'm moving my hands while I'm talking, my cat is attacking my arm. She thinks I'm playing with her. She's super goofy. Anyway, so that's what this means right here. As x increases without bounds, gets bigger and bigger, the graph approaches but doesn't reach the horizontal axis. As x gets super small, the graph will approach but never reach the horizontal axis. The horizontal axis is an asymptote. So again, I'm not going to ask you to give this back to me. I'm not going to ask you questions about this. Just trying to get you to be able to visualize. So the empirical rule applies here. So when we do the math, it's not exactly 60% that's within one standard deviation, but it is pretty close. And it's not exactly 95% that's within two standard deviations, but it is super, super close. And then once again, not exactly 99.7%, but it is also super, super close within three standard deviations. So we still have that 0.3% that's out in our tails. Okay, any questions about the normal curve before I move on? All righty. Here's our lovely empirical rule. I'm just going to let it sit here and we're going to marvel at its beauty for just a moment. Just marvel at how lovely it is. You all might have had nightmares about it, but it's my friend. I love the normal curve. Okay, there we go. All right. So we're going to take a look and kind of apply what I've just been talking about. And there's not a whole lot of math happening here. We're just going to kind of take a look at things and try to understand what's happening with this curve. So on the next slide, we have the height in inches of random sample of 50 two-year-old males. So a bunch of two-year-old boys, we got their heights. We're going to draw a histogram. Our class width is going to be 1. It's going to start at 31.5 inches and go up however high it is. So obviously, even though it says, do you think it's normally distributed? I probably wouldn't be using this as an example if it wasn't. So yes, it's going to be normally distributed. So here's the heights. We don't have to put them in the calculator or anything. Just marvel at how beautiful they are. Here's my histogram. Okay. So it is normally distributed. It looks pretty symmetric. Yes, this one is slightly lower than this one, but it doesn't have to be perfect. Statisticians don't deal in absolutes. It doesn't have to be perfect. But this, I can draw the curve over it, and it looks nice and bell-shaped. There's no obvious outliers. There's no obvious skew. It's a pretty nice normal curve. So any of you who have kids, you ever go to the doctor and they pull out this chart and they say that your kid's height is in the 50th percentile and their weight is in the 82nd percentile? This is what's happening. This normal curve thing is what's happening. They're looking at where it falls on this normal curve. If your kid is in the 50th percentile, he falls right there on the normal curve. If he's in the 97th percentile, he falls right there. 97th percentile is an outlier. It's more than 2 standard deviations away from the mean, right? This is exactly what's happening with those charts that they are using. They have standard deviation, they have the mean, and they have this chart created, and they just plot where your kid lands on this chart. This is exactly what's happening. Sorry, I get so excited about this stuff. It's, at least you don't have a teacher who hates math. I've had one of those before. It wasn't any fun at all. All right. So I already drew the thing over here. We're going to take a look specifically at this square, at this rectangle. I called it a square. Oh my gosh. Okay. We specifically about this rectangle right here. So if I find the area of this rectangle, it's going to be slightly, I could take, if I cut this off and put it into here, it's going to be pretty close to right under that curve, right? It's going to be really close to just filling in that area. Let me see if I colored this in right here. It's going to be pretty close to coloring that in. So if I find the area right there, so let's just do this. It's 1. This is 1, and then it's goes up to just about 20. So it's about a 20% probability that a randomly selected child is going to land in that spot right there. That's exactly what we are saying. And I'm going to give you better words here in a minute. Okay. So these are the two ways that we can talk about what's happening with that area. So I just calculated this area and I got 0.20, got a 20% chance the randomly selected individual being there. So if I calculate that area right there, these are two different things that it could mean. If I take that area, I can either mean that the proportion of the population with the characteristic described is that value, or can be described by that value. So I could say that about 20% of two-year-old males will be between that height. It will be between those two values, 34.5 to 35.5. So about 20% of two-year-old males are in that range. Okay. The second possibility is right here. The probability that a randomly selected individual from our population has that characteristic is described by that interval. So the other possibility is if I randomly selected a two-year-old male, I could, there's a 20% chance he's between 34.5 and 35.5 inches tall. We're going to do a giraffe problem that's going to have it all typed out for you. But these are the two ways we can describe it. We can either apply it to the population and say 20% of our population has that characteristic, or you can say, if I randomly select one individual, this is the probability they have that characteristic. Okay. So the weights of giraffes are approximately normally distributed with a mean of 2,200 pounds and a standard deviation of 200 pounds. Draw a normal curve with the parameters labeled. So I'm going to do that in a minute. And then shade the area under the curve to the left of the 2,100 pounds. Don't worry, I got that. And we're going to talk about the two different interpretations of this area, 0.3085. We're going to talk about the two different interpretations of that. So here we go. All right. So I shaded it. So my normal curve, here's where 2,100 pounds lies. It's right here on the normal curve. And then this area, I'm looking for this area right here. The lovely thing is that, so the only way to really calculate this area without fancy calculator tools is by using calculus. And it's actually kind of fun. And I might actually show it to my calculus class, because it's kind of fun. But you don't have to use calculus. We will have a fancy tool for you, a couple of them. And so the area under that curve is 0.3085. So about 30.85% of our curve is shaded in. So here's the two interpretations. The proportion of giraffes whose weight is less than 2,100 pounds is 0.3085. Or you could say 30.85%. I don't care how you do it. Uh-oh, that's not a pen. That is a highlighter. I don't care how you do it. Usually on the test, I will put like both answers with the percent and with the decimal. I'll put both of them as correct answers. So it doesn't matter to me unless I specifically say, leave your answer as a percent or leave it as a decimal. It doesn't matter to me how you answer it. My open math cares. I don't care. All right. So the next one is the probability that a randomly selected giraffe weighs less than 2,100 pounds is 0.3085 or 30.85%. So it really depends on, am I taking one random giraffe and want to know what the probability is that it weighs that much? Or am I trying to apply it to the entire population? These are the two ways to interpret that. Questions? All right. So I think that was my last slide. See, I told you this is the shortest one all term. So I want to warn you, chapter 7 in my open math, there's a couple, and I don't remember which problems they are. There's a couple of problems that tell you to round to a certain decimal place, and it doesn't really mean it. And I've been trying to fix it since I started teaching this class, and all I ended up doing was really messing up the problem. So, if it gives it to you, if it's wrong, and then after you use your 3 times or whatever, you realize that I had the right answer, it just was having me round wrong, send me a message and I'll just give you the points. And I don't mean to like stress you out or anything, but for some reason, a couple of the questions in chapter 7 are wonky with their rounding. So I don't want to stress you out. You could always try with your second guess if you're sure you're correct. You could always try like rounding to an 2 more decimal places or one less. But just letting you know there's some rounding issues in chapter 7, and it's kind of annoying. One of them you needed to round up. Okay. So you needed to go 1 more decimal out, or you just needed to round up instead of round down. Oh yeah, it was the one you sent me, right? Yeah, there was one of the ones that was, yes. Okay. Yeah, so just
Yeah, I ran into that too. It was like 0.245 was the answer or something, and it was, and they said 2 point or 0.255 or something like that. And I did every calculator. I mean, I have a picture of it in my phone. I don't have it on me, but I don't know what happened.
so if you have one of those, if you have one, chapter 7 is just wonky like that, and I haven't been able to fix it and figure out where the issue is. So if you end up with something weird like that, send me a message and I will either calculate it and be like, oh no, my open math is correct. Sorry about that. Or I'll give you the points. I have no problem doing the math myself and checking it and giving you the points. I don't mind. So if it's frustrating you, just send me the message.
Okay, it was in last week's chapter, but I still want to kind of send it to you. I want to show you to see if I was wrong.
Okay. Yeah, absolutely. And sending it to me through, you guys are doing this anyway, but send it to me through my open math because most of the time I can click on on your assignment and see the answers you put in. Sometimes it does things weird and it'll erase things, but most of the time I can just click on even the message you sent me and it'll take me directly to that problem and I can just see what's going on. So if you just click on the message instructor in my open math, of course I'll answer in Blackboard, but I'm happy to do the math and check it and be like, oh yeah, my open math is messed up. But it's a free program. When I was in college, the program that we had to use was $100. And every time you took a new class, you had to pay $100 again. So I'm really thankful that we have this flawed, my open math system that isn't super flawed, but just minor issues here and there. Free is so much better than $100. So that is the end of the lesson, but we're still on record. So if anybody has any questions, and it could be about final project proposals, it could be about hand in homework, chapter 6 homework, anything you like, now's the time to do that. Or you can wait until we're off recording. That's when the party.
So for the proposal, I had sent you my proposal, and I might send you another proposal just to like change. Not, it's kind of like the same one that I sent you, but it's gonna be a little different because I feel like, so you want 50 data points for each variable. So if you did, so I don't know why that's confusing me because I feel like I'm gonna have more than just like two, like an X and a Y. You know what I mean? I don't know. With,
It's
yeah.
So, okay, so for example, I'm gonna make this super simple and not a really good, this is not a great project idea. I'm just gonna make some things, and it could be a great project idea. I don't know. Make something super simple. I'm gonna weigh my cat every day for the next 20 days. What I'm gonna do is I'm gonna put one column is gonna be her weight for the day, and the other column is going to be how much food she ate in ounces that day. Those two things correspond with each other. That day's weight and that day's food intake. I'm going to do that for 50 days. And so I'm going to have 50 variables for, or 50 data values for each of them because I'm looking at 50 days, which obviously this is not a realistic thing, even though some people they could do the cat's weight and how many times they went into the litter box that day if they have one of those smart litter boxes, look at 50 days data. But I don't know what you're trying to answer. But anyway, so the 50 data values is generally it's like one thing that you ask two questions about. Looking at 50 different football players and how many or like maybe 50 different quarterbacks and their weight and how many yards they threw per game. I don't know.
Okay.
It's two things that correspond and you could have like five different data, things about them. Maybe you're comparing a lot of things, but like if you're running a linear regression, you're going to just choose two of them, but you could always, break it off. And I've had people do things like ask a question and have 50 people that they have two questions about, but then they will do something with all 50 and then they'll break it off and split male and female and do something different with it.
Okay.
Does that make sense at all?
Yeah. I'm just gonna wait for you to respond to the proposals, and we'll just, I guess, go back and forth until I figure out what's gonna work. Because I feel like I have too many variables at play. So,
Okay. And this is why I started doing the proposals. Originally, when I first started teaching this class, the proposal wasn't even part of it. And I didn't even know what people were doing until they got to after they collected their data and turned their data in. And at that point, you don't want to tell people, oh, by the way, this isn't going to work.
that's terrifying.
I threw this assignment on here, and I know this is going to be, you guys are going to think I'm so mean. I used to make it extra credit. But I found that like half the students weren't turning it in if it was extra credit. And then they would get to the data part of it, and I would have to say, this isn't going to work. So I was like, if I make it a real assignment worth real points, then more likely people are going to turn it in. And it worked. So this is the whole stats thing, right? The probability somebody's going to do the assignment if it's worth real points is higher. So yeah, so with this, and I will start tomorrow, I will start giving feedback, but it's going to take me a little while to get through them because I try to be somewhat thoughtful. So if you don't get feedback tomorrow, don't freak out. I will write some feedback for every single person. So just wait as I go through, and I try not to go through starting at the A's and going through because people with W last names end up getting like theirs very last. I try to cherry pick and just randomly choose people and just grade them that way, give feedback that way because it's kind of nicer.
I have a question in terms of our project proposals.
Yes.
I have a friend who previously took a class with you in Gunson. And so I've kind of run my every lab. I've been like, I've been thinking of this because she's really good at math. And I just want to make sure that like, if she thinks it's solid, I usually feel like it's solid. I initially was trying to come up with something that revolved around physical therapy because that's what I'm in school for, is to earn my bachelor's degree now so I can go off to my DPT school. But another one that she brought up, that like somebody in her class had done something with hiking, and I was like, ooh, okay, I hike all the time with my kids. And so my project proposal, it's not like, I didn't know how nicely you wanted us to put it. You did say that like we could submit a Word document if we didn't want to write in the box, but I heard you say two questions. So my project proposal plan was like to look at 10 hiking trails in Oregon and see if there's a correlation between the popularity of the hiking trail and the length of the hiking trail. Because for me, I go. If I see a pretty picture, I'm like, oh, I'm gonna go. I'm gonna go see this hike. I don't care how long it is. But I know for some people, length or elevation may correlate into whether they determine they even go on that hike in the first place.
See, I love that, but you're going to need to you'd have to look at 50 different hiking trails because you
Yep.
need, so That's the thing is
Hey,
you can't do just 10, you're going to need to look at 50 and maybe you won't, maybe you can branch out of Oregon even, you know, because
yeah, I know there's like over 1,000 in Oregon alone.
wow.
That's hey, please
I love that
stop.
idea. I love that idea to do, 50 different hiking trails. And are you going to do popularity by how many people visit it per year? Or,
Yes.
okay, I love that. That's a
Okay.
fantastic idea.
Okay. Thank you.
And yes, it doesn't have to be formal. You could just type, even like if she typed the exact words she just said, type those words in the box, just be a sentence and say, I'm really interested in moose and their pilgrimage. And I was thinking of doing something with the age of the moose and how many miles it traveled in his lifetime. Because clearly we can measure those things. Might jump in there and say, I don't know that you can can you realistically collect this data? Say, this sounds really great. Hey, let me throw other ideas at you. And I'm going to throw other ideas at you, but you don't have to take them. I might say, maybe you want to throw this third variable in there. But you don't have to. You don't have to take my suggestions. I just am going to throw stuff out. Something pops in my head, it's going to go into your feedback box.
No, that's perfect because I really, really want to do something like pertaining to exactly what my proposal is, but as long as it's like in that ballpark, that's perfect. So yeah, I'm anxious for that. Thank you.
You're welcome. All right, anyone else?
I have a question about proposals or project stuff too. That one, this has been like so stressful to try and come up with an idea and then also be able to find raw data. But being a dietitian, I was more thinking like number of daily bowel movements and quantity of or like percent of diet made up from ultra processed foods or something like that. And I can find all the clinical research that has already done the stats. I can't get the raw data. I know there are some databases out there, but you have to be a researcher and pay for access. So I don't know if you have any ideas. I ended up putting my proposal through for just correlating like average summer temperature and acres burned in the state of Oregon. But I could also only get data going back on the ODF site to 1993. So I don't have 50 years of data. So I thought I could maybe couple like precipitation, do 30 data points for precipitation and 30 data points for temperature. But what I'm understanding now is that won't work. I have to have 50 for each.
To break it down by quarter.
Oh, okay. I mean, I could see if I can find, and if you have any pointers for like finding that on the ODF website, I really struggled to find just data points on the internet for something that
So
was motivating.
some of the and this may not work for any of your ideas. And the thing is if you give me an idea and once I give you feedback, you're like, that's not going to work at all. You don't have to propose your next idea to me. Unless
Okay.
you want to. If you want to, you can send me a message and say, "Hey, my last one didn't work. I'm going to try this instead. Do you have any feedback?" And then I'll give you feedback on that. You don't have
Okay.
to. You're not stuck. It's not in stone. Once you send me a proposal, even after you collect your data, when you submit that, it's still not set in stone. It's not set
Well,
in stone until you turn in your final project.
so when you're saying collect like the temperature, the precipitation data quarterly, so then that would work. I'd only need I or maybe semi-annually and I'd only need 25 years. But then the fire data that I have only goes back to 1990 something, I think. That's the problem was the acres of fire burned on the ODF website. I can only get down to like 1990 something.
Okay, so I'm gonna, one of my favorite ways to get 50 data values here. So the states wouldn't be a variable, but many people do things by state. So whatever thing you're thinking of, almost always you can find like statewide results for things.
Okay.
So you could we have 50 states and you can go to each state and decide. You might even be able to find some like bulk data for the state for your nutrition things. It's possible.
Okay. I mean, that would be more fun for me, but also,
So I'm because
capacity to like dig too hard for.
some of the things that are like that are really big, like as far as like nutrition goes, is things like food deserts. Looking for at because there tends to be higher obesity rates in states with more food deserts. You know what a food desert is, obviously, right?
Yeah.
Okay. And then there's things like obesity rates and poverty. There's things like how many natural food stores are available, and then obesity rate. There's all of this stuff like that, and you can find that by state. Then there's your 50 data values, one for each state. So it's not
Okay.
the raw data, but it's per state data. So it makes it raw enough.
Okay. Yeah. Obesity rate per state, and then, economic data. I get. Okay. All right.
And
Maybe coupling that with economic
trying
data.
nutrition stuff with that.
Okay.
And I mean, if you just start searching, Googling random things about nutrition and start seeing, hey, what can I find per state? What is something easy to find by state?
Okay. Thank you.
I love things if it's something you're passionate about, you are going to put more of yourself into the project.
Yeah. Thanks.
All right. Anyone else? Okay, I'm going to turn off the recording. Everybody got, and you guys maybe forgot you were being